Welcome back, everyone. We have officially reached week 7 of programming for computer interfaces. In last lecture, we focused on UR, which is great for a simple one-on-one conversation between two devices. But as your engineering project grow, they get more crowded. You might have a sensor for temperature, a display to show result, and extra memory to store the data, all needing to talk to your microcontroller at once. Think of it this way. UR was like a private phone call between two friends. It's simple, but if you want to talk to five people, you need five separate phones and 10 separate wires. Synchronous protocol this week are like a professional boardroom meeting. In this boardroom, we have one master, which is your microcontroller, who runs the meeting, and several slave devices, which is your sensors and display who listen. To make sure nobody talks over each other and that everyone stays perfectly on time, we use a shared clock, basically a metronome that keeps the whole group in sync. By the end of today, you will know how to manage this digital meeting using I2C and SPI so your project can handle multiple devices without a spaghetti mess of wiring. Let's dive in. In previous week, we utilized UART for basic point-to-point communication. It was effective for simple tasks, but as your engineering system grow in complexity, you will find that you need protocol capable of supporting multiple devices sharing the same data lines. Look at the comparison on the slide. Asynchronous or UART. This is the peer-to-peer relationship. There's no shared clock signals. So the device must agree on that timing beforehand using a baud rate. Synchronous, they use in I2C and SPI. This introduces a master, which is your microcontroller, that dictates the timing for everyone else. Think of the difference like this. Asynchronous is like two people trying to clap in unison in total darkness. They have to hope their internal sense of rhythm is exactly the same, or they will eventually fall out of sync. While the synchronous is like a marching band, where the master is the drum major and the dedicated clock line SCL or SCK is the beat of the drum. Because every sensor in the system follows the same beat, the master can synchronize data sampling perfectly, allowing for much higher data density and faster speed. The key takeaway is that synchronous protocol use that clock signal to ensure everyone is in step, which is how we manage a network of sensors rather than just a single conversation. I2C stands for Inter-Integrated Circuit, but you will often hear it called the two-wire interface because, quite literally, it only needs two main lines to talk to dozens of different devices. Look at the architecture on the slide. We have SCL, serial clock. This is the heartbeat of the system. The master drives this line to keep every sensor in the room perfectly synchronized. Second, we have SDA, serial data. This is the actual content of the conversation. Unlike UART, the single wire is bidirectional, meaning the data can flow from master to the sensor or the sensor back to the master. Now notice two zigzag symbols at the top. So the pull-up resistor. This leads us to a clever engineering concept called open drain design. Imagine you have a long rope hanging from the ceiling of this lecture hall, held up by a spring. Because of that spring, which is the pull-up resistor, the rope naturally sits high up near the ceiling. This is our default high state, which is 3.3 volt. If I, the master, or any of you, the slave, want to say something, We don't push electricity onto the wire. We simply reach up, grab the rope, and pull it down to the floor to create a logic 0. When we let go, the spring will pull it back up to the logic 1. This is brilliant because it prevents a tug of war. If two of you pull the rope at the same time, the rope just stays on the floor. Nothing breaks and no chips get fried. Just remember, if you forgot to pull up register in your lab, the rope will just lay on the floor and your picker will think the line is dead. Now, if everyone in this room is connected to the same rope, which is the SDA line, how does the master make sure that a command intended for the display isn't accidentally picked up by the temperature sensor? The answer is addressing. I2C relies on a unique 7-bit address to identify every target peripherals. Think of it like me standing in front of this class. If I just shout, "Open your books," everyone's confused. But if I say, "Martin, open your book," everyone in the room hears me. But only Martin actually takes action because he recognizes his address. Look at how this looks in the data frame. In start condition, the master pulls the SDA line low while the clock is still high. This is like me clearing my throat to get the room's attention. Then we have a 7-bit address where the master calls out a hexadecimal code. For example, 0x76. Every sensor on the bus will hear it, but they are all programmed to ignore it unless it matches their specific identity. Then we have ACK, acknowledgement. This is a critical step. The specific sensor whose name was called pulls the SDA line low for 1 clock pulse. This is like a student raising their hand to say, "I'm listening, sir." Then we have a data byte. Only after that handshake do we send the actual 8 bits of information. And lastly, we have a stop condition where the master will release the line back to their default high state and then the meeting is adjourned. There's one important engineering trade-off here: protocol overhead. Because the master has to call a name before every single piece of data, we will lose some speed. It is the tax that we have to pay for being able to use only 2 wires to talk to many different devices. Now that we understand the rules of the meetings, let's look at how we actually book the boardroom using MicroPython code. We use the machine library again, but this time we import the I2C and pin classes. Look at the anatomy of this initialization line. I2C equal to I2C 0, SCL equal to pin 5, SD equal to pin 4, and lastly the frequency is equal to 400,000. Let's do some analysis. Okay. First, we have the hardware block ID. Just like the UART, the Pico has 2 internal I2C engines. Choosing 0 is like picking which specific meeting room in the building you want to use. Next, we have the pin mapping for SCL and SDA. This tells the Pico exactly where the clock rope and the data rope are plugged in. If you plug your sensor into GP4 and GP5, but your code says something else, the Pico will be shouting into an empty room. Next, we have the bus speed, where we set the frequency to 400,000. This is the speed of the conversation. We usually have 2 gears, 100 kHz for a slow, steady talk in standard mode, or 400 kHz for a fast-paced, fast mode discussion. Once you set the rule, there is one magic command every engineer should run first, which is I2C.scan. So how I2C scan works? So this is like me standing at the front of the room and asking, "Is everyone here? Shout out your ID number." The Pico sends a signal to every possible address. If a sensor is correctly wired and powered, it will reply and its address will appear in your terminal. If your scan returns an empty list, you know your ropes aren't connected properly before you even start writing the rest of your code. Now, if I2C is the minimalist choice with just two wires, SPI, Serial Peripheral Interface, is the speed demon of the engineering world. We use SPI when we need high bandwidth. Think of tasks like updating high-resolution images on a TFT OLED display, reading large file from the SD card, or streaming audio. Look at the high-speed data pipeline on the slide. We have four main wires. We have SCK, the serial clock. This is the master-driven heartbeat that keeps the data moving in perfect time. We have COPI, controller out, peripheral in. This is the master mouth talking to the slave ear. We have CIPO, controller in, peripheral out, the slave mouth that talk back to the master. And we have CS, which is the chip select. This is the traffic director. In I2C, we were all on one phone line and had to waste time calling out names to start conversation. While SPI is like having a private intercom switch for every student in this room. When I want to talk to slave number 1, I pull the specific CS1 pin low. This is called active low. What wakes them up? While the switch is down, we have a private lightning fast conversation. Everyone else sees their switch is still high and completely ignore the bus. The benefit, it is incredibly fast because there is zero addressing overhead. We don't waste time calling names, but the downside is it is wire heavy. If you have 5 sensors, you need to have 5 separate CS wire coming off your Pico. It is a classic engineering trade-off. You sacrifice physical pins for raw speed. Now, this is where the SPI gets truly unique. While UR and I2C are mostly half duplex, meaning it's like a walkie-talkie where you have to wait for one person to finish before the other can speak. SPI is full duplex. This means data is being sent and received at the exact same moment on every single clock pulse. Look at the image on the slide. It uses gears to represent the internal shift register of the chips. Now, imagine two people standing face to face, each holding a suitcase. Every time a metronome clicks, that's our SCK, they both push their suitcase forward and catch the other person's suitcase at the exact same time. No one is ever waiting for a turn to talk. This constant trade of information happens over the COPI and CIPO lines simultaneously. However, for this high-speed handoff to work, our hand must be perfectly aligned. So this is task of the configuration match. First one is the polarity, C-pole. So does our metronome start its beats in the up position or the down position? So it is the task of either the clock is either high or low. Second, we have phase, CPHA. So in this case, or in this mode, do we grab the suitcase on the very first beat or the second beat? So do we sample the leading or the trailing edge? So if these settings don't match perfectly between your Pico and your sensor, what will happen? You'll be reaching to a suitcase that hasn't been pushed yet, and your data will be turned into gibberish. This is why the first thing you should do in any project is check the sensor datasheet for its required SPI mode. Now let's put this gear into motion with some code. Just like with I2C, we use the machine library to set up our SPI interface. Look at the initialization. SPI equal to SPI 0, baud rate equal to 100,000, polarity equal to 0, phase equal to 0, SCK equal to pin number 2, MOSI equal to pin number 3, MISO equal to pin number 4. So unlike our UR or I2C, notice the baud rate here is, sorry, The baud rate is 1 million or 1 megahertz. So SPI can easily run at 10 megahertz or more. That is like jumping from a bicycle to a bullet train. The gear or the mode, polarity and phase. Here is where you tell the Pico which SPI mode to use. Remember, this must match the sensor datasheet perfectly, or what will happen, you'll be grabbing the suitcase that aren't there. Then the pin mapping. So we define our clock, our MOSI or COPI, and our ear MISO or CIPO. But there is most important part of SPI coding, which is the manual control. In I2C, the hardware was like an automated receptionist who call out names for you. While in SPI, you are the receptionist. You have to manually flip the switch for the specific device you want to talk to. Look at the transaction cycle in the code. Select device. So we use cs.value equals 0. So because the chip select is active low, so pulling it to the floor tells the specific sensor, wake up, I'm talking to you. Then we have a send or receive with using SPI write. So we run SPI write to exchange our data. Then lastly, we have a deselect device, which is cs.value equal to 1. So what will happen after we completely send our data, then we hang up the private intercom so the bus will be free again for others to use. So what happens if you forgot to pull the CS line back to high? The sensor will stay awake and might interfere with the net conversation you try to start. Now, as future engineers, your job isn't just to make things work. It is to choose the best tool for the job. You often find yourself at a crossroad. Do I use the simple two-way approach? Or do I have to go for raw power? This is the ultimate battle. I2C versus SPI. Think of I2C is like the office group chat. So the pros is it is incredibly wire efficient. You need 2 wires no matter how many devices you add. It is very easy to scale. You just assign a new address to a new node and plug it in. Most importantly, it has a built-in read receipt, which is the ACK bit, so the master will know the message actually arrived. The cons is it is slower than the two. It's maxing out around 400 kilohertz because the master has to waste time typing out everyone's name because sending the actual message. And it is best for a small, low speed sensor like temperature or humidity sensor. SPI on the other hand is like a dedicated high-speed private tunnel. The pros is it is built for pure performance, reaching speeds out of up until 10 megahertz or more. Because it is full duplex, it can send and receive at the exact same moment without pausing to take turns. But the cons is it is wire heavy. So for every new device you add, you have to run a new dedicated chip select wire back to the Pico. It also has no read receipt, which is no ACK. So it is a fire and forget protocol, meaning that if the wire is loose, the master will never know. And it is best for heavy lifter like TFT display, SD card, or high fidelity audio systems. So the next time you design a system, ask yourself first, do I need to save space on my board? So choose I2C. Or do I need my data to move at the speed of light? Then you choose SPI. Engineering is really about getting it right for the first times. It's about having the tools to figure out why it went wrong. When your communication bus stays silent, don't panic. Just entering the investigation phase. Let's look at the 4 most common crime scenes you'll encounter in the lab today. First is the ghost town. OS error. Error number 5. EIO. This is the most famous error in I2C. It stands for an input-output error, and it means the master shouted a name into the room and nobody answered. So it's like calling out student's name in this hall during lecture only to realize that sadly their seat is empty. The fix, First, check your wiring integrity. Is the sensor actually getting 3.3 volt? Second, check your pull-up resistor. Without them, the signal is dead. And finally, recheck the address. Are you calling the right name? Next is the swap mouth and ear. I2C.scans return empty value. If your scan comes back with empty list, your hardware is probably fine, but your signal are crossed. Imagine you're trying to listen with your mouth and talk with your ear. The physics just don't work. Try reversing your SD and SL connection. It is the most common mistake in the lab and it is a 5-second fix. Then next is the radio static SPI garbage data. If you're using SPI and number on your screen look like a random symbols or garbage, your timing is out of sync. This is a polarity of phase mismatch. It's like trying to tune into a radio station that is slightly off frequency. You will hear noise, but you can't understand the words. So the fix is go back to your code and check your polarity and phase settings against the sensor datasheet. The last one is the open mic freeze. If your device won't work exactly in one command and then completely freeze for the whole systems, you have left the line busy. So it's like finishing your speech but forgetting to turn off the microphone. No one else can speak because you are still holding the floor. So what you can do in SPI, you must ensure the chip select pin is pulled high immediately after your transaction ends to release the bus. Keep this checklist handy because it important for you as a reference when you do the lab later on. We have covered a lot of ground today. We have officially moved from simple one-on-one phone calls of UR to the professional boardroom meetings of I2C and the high-speed tunnels of SPI. Before you head out to the lab, let's look at the 3 big ideas to keep you in your engineering toolkit. First, coordination is the key. Synchronous protocol use shared clock to make sure the master and slave are always in step during a data transfer. Second, the right tools for the job. You know that the I2C is a minimalist. It saves you pins by using only 2 wires but costs a bit of speed due to address overhead. While SPI is the speed demon, it gives you a full duplex power but require a bit more spaghetti or wiring or wire in your wiring. Next is the software advantage. Don't forget that MicroPython's machine library is doing the heavy lifting by abstracting away all that complex low-level timing for you. So the roadmap ahead, we are building your skills brick by brick. So in the previous week, you learned how to make 2 device talk by using UR. And this week, you learned how to read data from multiple sensors at once using synchronous protocols. But what happens if your Pico loses power? All that beautiful data vanish. Poof. That is why in the next or in the coming week, we are moving into data logging. We will learn about file system and how to save your sensor reading into a CSV file so that your data will survive even after the plug is pulled. Thank you for your attention. Great job today, everyone. I'll see you in the next lecture.